community as a way to stand up for population rights or a particular aspect of environmental health that's being threatened by certain types of agriculture. And so with that, our time is up, and I really appreciate your attention this morning. I wish all of you the best. Look forward to talking to you in the future. Thank you for being part of this webinar.
またはカードを入れてください。クレジットカードはご利用できません。踊りは
To have you here today to hear our lectureship award recipient, Jennifer Doudna. Dr. Doudna is a Howard Hughes medical investigator. She's professor of chemistry and molecular and cellular biology at UC Berkeley, and she also holds the Li Ka-shing Chancellor's Chair in Biomedical Sciences. Dr. Doudna, welcome to UCLA. We're excited to hear about your amazing work that's changing not only biology but probably society. The annual lectureship is a long-standing tradition of the School of Medicine that reinforces the importance of scientific exchange and breakthrough discoveries in biomedical science. The essence of a great university is discovering new ideas, new knowledge, all of which benefit society. Innovators like Dr. Doudna embody all these goals and are the quintessential expression of human curiosity. So your program says that Interim Dean Kelsey Martin is going to introduce Dr. Doudna, but we changed that, and I'd like to ask Doug Black, professor of microbiology, immunology, and molecular genetics, an expert on RNA biology. I feel like I'm introducing Bill Gates or something. It's really my pleasure, great pleasure, I think, to introduce my long-term colleague, Jennifer Doudna, for the school lectureship. Jennifer really, I think she can only be described as one of the most admired and influential scientists in RNA biology. And I think I'm going to skip the long list of Academy elections and breakthrough prizes and so on, and try to say something about her science and really some of the science that led up to what she's doing now, which all of you are most familiar with. So Jennifer actually is from Hawaii. She grew up in Hawaii and came to stateside to go to college. She went to Pomona College, close here, and then went on to do her PhD at Harvard Medical School in Jack Sosak's lab. And at Harvard, she really pioneered the entry of the Sosak lab into ribosomology and the study of the early RNA world. And I think that's where she got her start in RNA biology and interest in this stuff with her. And she went on to do her postdoc with Tom Scheck in Colorado, studying the structure and entomology of RNA again. And she took this work with her when she started her own lab at Yale in 1994, where soon after she determined and published the structure of the P4P6 domain of group 1 intron. And this result, it seems long ago now, but it's hard to really overstate its impact on the RNA field. It was the largest RNA structure that had been solved to date, quite a bit larger than the long-studied tRNAs. And within this structure, it illuminated a number of structural features and principles of RNA folding that are really now commonly held principles in the study of RNA functions and folding. So Jennifer moved to Berkeley in 2002, and her positions were described by the dean. And at Berkeley, she has been continuing her studies of riboscience and RNA biology and biochemistry, but she's also branched out into many other areas of RNA biology. She's worked on areas of translational control, viral iris function, entomology of the RNA interference pathway, visiting some of the more larger projects. And through this, she's trained many scientists and leaders in all of those fields. And so if I were to try to describe, Jennifer's kind of special style and traits of science, I would say that for all of this work, just really this is a remarkable skill for seeing what the key information that's needed to drive the field forward. What experimental approach on the graphic and structural analysis will really break and change the question that this team has. I think it's a rare talent that the other presenting of the talent is so sharp. So a number of years ago, Jennifer became interested in the mechanisms of hosted systems and bacteria, and in particular, the enzymes and gene products that are coded in what were called CRISPR loci, mediated bacterial resistance to infection. And so what you assume from those studies, I think, is a lot of great illustrations of how basic research is interesting, but maybe not particularly mainstream biological questions can have an absolutely pervasive impact on these larger fields of science and medicine that some of us are now aware of how they affect these projects. So if you read just a small amount about the history of these projects,
The doors on the right side will open.
Jennifer's lab went on.
Please change it for the Yamamoto line, the Sobu Tojo line, the Seibu Traditional line, the Yamamoto Sobu line, the Yuraku Sobu line, and the Kikuchi Sobu line.
The targeting sequences and other quite fascinating aspects of CRISPR biology. So finally, then, I think I need to comment that powerful new technologies raise questions for society and their appropriate use. Jennifer has been at the forefront of calling for public discussion of how these tools should be used. So what's an appropriate use of this technology? How genome editing might be used usefully, and how perhaps it shouldn't be used. And so these kinds of discussions, these public discussions, were reached a milestone last week at a remarkable meeting at the National Academy, where many of the stakeholders and interested parties met. A meeting that Jennifer was really instrumental in organizing. So you can see then that there's much for Jennifer to tell us about, and before I bring her up here to talk about her talk, the deans are going to come up, Dean Nesbitt and Martin. Is it now? You weren't moving, I was working. And Jennifer.
So we're really delighted to present you with the 56th annual lecture at Chip Awards in the School of Medicine. Here you go. The big step. I really appreciate that, and it's been a great day here. And I think, it's always a great pleasure to see a lot of students here, because I think that this work, as I'll tell you about today, and you heard a little bit about in the introduction, is a great example of how your own curiosity about nature and how biology works can lead you in unexpected directions. I have to say, over the course of my career so far, that's really been my experience. It's just by following what I thought was interesting, and of course what my students thought was interesting, it sort of led us in directions that I never could have anticipated, including the story that I'll tell you about today. So what I thought I would do today is really tell you about the origins of the CRISPR biology research in our own lab and how it led us to thinking about this as a technology for genome engineering. And then I want to tell you a bit about how this actually works, because we're really a lab that focuses on molecules and mechanisms. We like to understand how these kinds of activities occur in cells. And then I'll tell you a bit about where I think this is going in terms of its application in the clinic. And then at the end, I want to come back to this point that Doug made at the end about the ethics of genome editing and where this is going in the future. So I want to really start by just pointing out that, if you could even a few years ago, if you thought about the ability to change the DNA sequence in a cell in a very precise fashion, it was still in the realm of science fiction. In fact, I remember seeing that in Boston in the 1980s, when Peter Durbin and others were actually already thinking about how you could actually do this in the context of the genome of an entire cell. And the challenge really was that you envision a way to make a very precise change in the DNA sequence so precise that you might be able to change a single base pair. And that's actually the entire genome of, say, a cell, and be able to fix a mutation that could otherwise cause disease because of
Please put your mobile phone
very analogous to being able to make a very precise change to a document word processing program. And for us, the path to this kind of technology actually came about through our effort to understand how bacteria fight the flu. And I noticed that my resolution is cutting off the bottom of the slide. Should I try to change that or not? I do risky. So I'll read you the bottom of the slide. But basically, it's a curiosity about how bacteria fight viral infections. And so I want to tell you, I'm going to do three things today. I want to talk about how we got from studying, as I said, kind of a somewhat obscure area of biology into a biotechnology. And then I want to tell you a bit about how this technology actually works from the standpoint of the molecules involved. And then at the end, I'm going to come back to this question of how we think about using this technology both in clinic and also from a bioethical perspective. So for us, the CRISPR systems really came first to my attention about 10 years ago, when a colleague of mine, who's in the picture, unfortunately not showing on the slide, but Julia Mansfield, who's a very well-known scientist at UC Berkeley, called me up one day, and her lab does metagenomic sequencing of bacterial genomes. And she contacted me because she said, we're seeing a very unusual sequence signature in the genomes of many of the bacteria that we're investigating. And mostly these are bacteria that have never been cultured, never even been identified. And in her research, they were coming across not only these bacterial genomic sequences, but also the viruses that infect these organisms. And what was very, very interesting was that a number of these bugs had a repetitive DNA sequence in the genome that consisted of a sequence of DNA, typically 40 base pairs or so in length, that was repeated over and over in the genome. And what was very interesting was that in between these DNA repeats were sequences that were derived from viruses. Again, these sequences were 30 to 40 base pairs in length. And what's not showing here is three papers that were published in 2005 from three different bioinformatics groups that all pointed out that this sort of sequence, this signature, had the characteristics of some kind of a system in bacteria. These were conserved, and the fact that bits of viral sequence were being integrated into the bacterial genome, sort of made people start to wonder if this was some kind of acquired immune system in bacteria. And what was also interesting was that adjacent in the genome were typically CRISPR-associated or Cas genes. DNA sequences. So it looked like some kind of a system, and these had come to be called clusters of regularly interspaced short palindromic repeats or CRISPRs. So these sequences right here, signatures of what emerged that came to be known and understood as a bacterial organism. So why did Jill call me? Well, she called me because, as Doug mentioned, we've had a long-standing interest in my lab in understanding how RNA molecules are used in cells to control the expression of information in the genome. And one hypothesis at the time was that maybe these sequences were actually operating at the level of RNA. In other words, the cell might be making an RNA copy of these sequences and then using those RNA molecules to help find matching viral sequences, much the way eukaryotic cells use a process called RNA interference. So we began sort of playing around with these systems, and what emerged over the next several years, and sort of another interesting twist about the biology here, was really initially